Have you ever looked at a simple fraction and thought, how on earth could that create a graph that looks so wild and complicated? Well, that's the whole magic of rational functions. Today, we're not going to treat this like some dry math class. Nope, we're going to treat it like a puzzle where one single simple rule creates these incredibly intricate and honestly pretty beautiful results. So let's get into it. I mean, just look at this. You've got curves shooting off to infinity, weird gaps in the line, and these invisible walls the graph just refuses to cross. But the engine driving all of this chaos? It's just a fraction. So the big question for us today is how? How does a simple division problem produce a picture with this much drama? Let's investigate. To solve this puzzle, we have to start at the very beginning with the one principle that controls everything. You can think of it as the core idea, the one unbreakable rule that dictates every single twist and turn you see on that graph. Okay, so this whole idea isn't as foreign as it might seem. You already get the basics. On the left, you've got a rational number. You know, a simple fraction, like 3/4. On the right, we have a rational function. It's the exact same concept, just leveled up. Instead of plain old numbers, we're now dividing one polynomial, p of x, by another polynomial, q of x. And here's the formal textbook definition. A rational function is just a function that's a ratio of two polynomials. That's it. That's the entire DNA of the thing. But as we are about to find out, that simple definition has some pretty huge consequences. And here it is. This is the big one, the unbreakable rule. The one constraint that creates all the fascinating behavior we see. You can't divide by zero. Ever. It's the cardinal sin of math, right? So that means any x value that makes our denominator, q of x, equal to 0 is totally off limits. This one rule is the reason for all the breaks and boundaries we saw earlier. So this one rule creates what I like to call forbidden zones on the graph. The function just can't exist there. So what happens when we get close to them? This is where our investigation gets really interesting, because the consequences of getting near these zones are what shape the entire graph. As our x value creeps closer and closer to a number that makes the denominator 0, the graph has no choice. It has to break. It's mathematically impossible for it to continue. We call these breaks discontinuities, and it turns out they come in two main flavors, which are basically the key clues we need to solve our puzzle. So our first clue pops up when we start factoring the top and bottom polynomials. Let's ask ourselves, what happens if there's a factor in the denominator that doesn't have a matching partner up top to cancel it out? Well, this leads to our first and probably most dramatic type of break. It creates a vertical asymptote. The best way to think about this is like an invisible electric fence. The graph will get infinitely close to this line. It'll either skyrocket up to positive infinity or plummet down to negative infinity. But it can never, ever touch or cross that fence. And you'll find these fences at any x value that makes the simplified denominator equal to 0. All right, on to clue number 2. What if the opposite happens? What if a factor in the denominator does have an identical twin in the numerator? Well, they cancel each other out, obviously. But this creates a much more subtle and totally different kind of break in our graph. This creates what we call a hole. It's not a giant electric fence. It's more like a tiny little pothole in an otherwise perfectly smooth road. The graph looks like it's cruising along just fine, but then there's just one single, solitary point that's missing. And you'll find that hole at the x value that made that canceled factor equal to 0. Okay, so we've investigated the forbidden zones and the breaks they cause. Now, let's zoom out. Let's look at the big picture. What does the graph do way, way out on the edges when x gets ridiculously big or ridiculously small? Where is this thing headed in the long run? See, as x shoots off towards infinity, the function doesn't just wander around randomly. It actually starts to follow a really predictable path, like it's locking onto a set of guiding rails. And these guiding rails are also asymptotes. But instead of being vertical, they're either horizontal or, in some special cases, slanted. And finding these guiding rails is actually way easier than it sounds. It all boils down to comparing the highest power of x, what we call the degree, on the top and the bottom. If the bottom's degree is bigger, the rail is the line y equals 0. Easy. If the degrees are a tie, the rail is just the ratio of the leading coefficients. And if the top's degree is bigger, well, there's no horizontal rail, which opens up a whole other possibility. So what happens when the numerator's degree is bigger? Well, there's a really cool special case. As the folks at Purple Math put it, If the numerator's degree is exactly 1 more than the denominator's, the graph starts to behave roughly like a slanty straight line. And this is exactly what that looks like. We call it a slant asymptote. It's a tilted, guiding rail that the graph gets closer and closer to as x gets huge. And to find the exact equation for that tilted line, you just have to do a little polynomial long division. The answer you get from the division is the equation of the line. Pretty cool, right? All right, detective. We have gathered all of our clues. We've got the potholes, the vertical electric fences, and the long-range guiding rails. Now it's time for the big reveal. Let's assemble all these pieces and sketch the full picture of our function. And here's our game plan. It's a 6-step process. First step, we simplify the function and find any of those holes. Then we find where the graph crosses the axes, the intercepts. After that, we draw in our vertical asymptotes. Step 4, we figure out the end behavior, that horizontal or slant asymptote. Then we plot just a few extra points to be sure. And finally, we connect the dots and sketch our curve. So let's see it in action. Over on the left, that's all our algebraic detective work, finding the vertical asymptotes, the horizontal one, the intercepts. Then on the right, you can see how each of those clues gets placed onto the graph. The dotted lines are our boundaries, the point is our intercept. This framework basically tells us exactly where the curve has to live. Now, understanding the graph isn't just about making pretty pictures. It is absolutely critical for the final piece of our puzzle, making sure we can correctly solve equations that have these functions in them. And this brings us to a huge classic mistake. When you're solving one of these equations, it's easy to do all the algebra perfectly and get an answer. But what if that answer you found is actually one of the x values that lives in a forbidden zone? You know, a value that makes the original denominator 0? This is what's known as an extraneous solution. Think of it like a ghost solution. It looks real, your algebra says it's real, but it's an illusion. It's invalid because it breaks our one unbreakable rule. You cannot divide by 0. So you always have to check your answers against the original equation to make sure they're not in a forbidden zone. Which brings us all the way back to where we started. What seemed like just a simple fraction turned out to be this incredible puzzle filled with invisible fences, hidden potholes, and secret guiding rails. It just goes to show you that even in math, sometimes the simplest rules can create the most beautiful and complex results. You just have to know how to look for the clues.